So today we're going to be talking about systems of equations. Actually, it's the first part of systems of equations. So the topic is systems of equations. In systems of equations, so this is chapter 10 from a new book. It includes two topics. So the first one, which is the one that we're going to finish today, start to finish today, is seemingly unrelated regression. That's called SUR, and simultaneous equation model. Simultaneous equation model. This is again. So today's lecture is gonna deal with SUR. Now, relative to what we've been talking about so far in class, is that basically when we're talking about seemingly unrelated regression or simultaneous equation model, for that matter, is that instead of having one equation, we have now multiple equations. So we have multiple equations. Well, we only talk about one equation. So for example, we can have one equation, one dependent variable and one set of explanatory variables with errors, a second equation with set of explanatory variables and errors, and up to n equations. Okay, so and we have to be a little bit careful with notation here because remember before this index I used to refer to number of individuals, now we're using it to refer to equations. Or another way to write it is yi equals to xi delta I di. So here we have d by 1 observations, xi should be d by ki, and here the index ki is because the number of explanatory variables of each equation might differ. I we have a k by 1 coefficient, and the other term is d by 1. The number of equations go from 1 to n. Okay, so here in terms of the notation, n is the number of equations, t is the observations for each equation, ki corresponds to the parameters in each equation, or the number of explanatory variables in each equation. It's going to be hopefully I cannot see it. Ki is the number of explanatory variables on each equation. Okay, so that's the game. So what we have is multiple equations with different explanatory variables, where each equation has its dependent variables, explanatory variables, its coefficients, and its errors. Okay, so as an example, something I'm very familiar with, that's kind of one of my main areas of research, demand model estimation, demand system estimation as a matter of fact. So let's say we have the demand model, demand system, where I So the I, for each equation will correspond to one good in the demand system. So for example, I've estimated demand systems where, the first good was food of services. We also have medical care. We have housing, and we say that we have other types of goods and services. Okay, so that's a typical example. So in this example, the yi, usually in demand systems, instead, even though, like usually the theoretical model, we have qi as the quantity demanded. In demand systems, yi correspond to expenditures or shares. So the yi's are the shares or the proportion of, of income or total expenditures on food. So there are the shares or expenditures in dollars. And again, in the demand system, the xi's are going to include the prices of all goods and income. Well, it will be here the prices of all goods in the system. Okay, and income. Okay, so in terms of equation form, we're going to be writing a system. So, we're going to have one equation for food as a function of price for food. It should be the price for medical care, the price for housing, the price for other income, and the return. Now, here I'm saying a function, but usually it's a linear function to make our life easier. But that's kind of like the structure of the system. So we'll need another equation for medical care. Again, it's going to be a function of those same coefficients. This is error, first error. This is going to be the second error. We're going to have another equation for housing. Again, it's going to be a function of exactly the same variables. It's error term. And we'll have another equation for other goods. Okay, so that's basically what you have. So if you think about in terms of the type of data that you have, we can have cross-sectional data, and in this cross-sectional data, say we have 1,000 individuals, and for each individual, we have how much they spend on food, and what are the prices of, that this specific individual, and actually we have, I said, 1,000 individuals, the prices that each of those individuals have for food, medical care, housing, other goods, and income. And the same thing, information about medical care, housing, and other goods and services. So basically, the idea here is that we have four equations, and we need to be estimated the demand, and we need to estimate the coefficients for each of these equations. Okay, so that's kind of like the general, setup. Now, to denote that, let me write a little bit of notation. So you see, for each equation, remember what we're going to have right now is that for each equation, we're going to have T observation. So remember, I now corresponds to equation, and the second coefficient is going to correspond to individual or observation. Okay, so it's good to have that in mind, to have in your mind. And with the error term, it's going to be exactly the same thing. we have in these terms for the equation I, we're going to have t different error terms. And again, I, the first coefficient corresponds to the equation, and the second one corresponds to individual. And it's easier to think in terms of individual. So for our matrix xi, it will be a little bit more complicated because we're going to have xi11, so on and so forth, xi1ki. Remember that I corresponds to the equation. The second index is going to correspond to the number of explanatory variables. So this is going to be the first explanatory variable. And the last index will correspond to the individual. Okay? So again, as you have that in mind, I mean, the notation again changes a little bit. So remember, in the context of SUR, the first index is going to refer to the equation, and the second index is going to correspond to the individual for the yi and the ai. And in the context of the explanatory variables, well, I mean, usually we're not going to need to explain to go to the level of detail of while we look for each explanatory variable. But you want to be thinking in terms of how does the data look in the context of Excel. I mean, it's good that I explain you what the type of data that you need in this case. Okay. Now let's talk about the model assumption for SUR. And so these are all of these model assumptions can be relaxed, but the basic model is a model that satisfies the exogeneity assumption. So the expected value, and that includes all the errors, conditional on the values of the explanatory variables for all of the equations equal to 0. So that's the exogeneity condition. So in here, basically that error, this BE here, it actually includes the errors for all of the equations of the Riemann system. Okay, so that's kind of what that includes. So it's kind of like a stronger form of exogeneity if you want to think about it, because the errors are not correlated with any of the explanatory variables in the system of equations. The second assumption again, so the exogenating, of course, it can be relaxed. We can estimate in a SUR system for endogeneity, but for the basic model, it's better. It makes our life easier to understand what's going on if we also assume this that these assumptions are satisfied. The second one is homoscedasticity, and this is an equation by equation type of homoscedasticity. So we're saying that within each equation we have homoscedastic errors. We have expected value of the errors or the product of the errors within each equation. Well, conditional on the values of explanatory variables for all of the equations is equal to a constant times I. Remember, this is t by t. Okay, so basically what we're saying is that the errors are homoscedastic within each equation. And the assumption that it's kind of like the key, I would argue this is the key SUR assumption, has to do with the correlation of the errors across equations. And the main assumption is that these two balances of errors are uncorrelated across observations across observations but correlated across equations. That is kind of the key SUR assumption. Uncorrelated across observations but correlated across equations. And let me write it down mathematically, and then I'll try to give you some intuition. And then, I can also show you the structure of the variance covariance matrix in the SUR model, which I think gives you a lot of intuition. So basically, here's what we have. So here we're saying is that the errors AIT and AJS errors conditional on xi to xn are equal to sigma ij if t is equal to s and 0 otherwise. Okay, so this seems to be kind of complicated, but actually it's very simple. So again, let's think about it. So remember, I and j here, those correspond to different equations. Okay, so we're saying that the errors for different equations are correlated, correlated if we're talking about the same individual. Okay, that they are uncorrelated otherwise, which basically means P different than S, if we're talking about different individuals. So remember, here the idea is that we have, so here, we're talking about cross-sectional data, okay? So we can use the observations for all of the individuals to estimate one equation. And so remember, within the context of cross-sectional data, we're assuming that there is no correlation across individuals. We have some sort of random sample from a big population, so each individual is independent from each other. Okay? But now remember that we're estimating another equation for the same group of individuals. So what we're saying here is that, again, the observation for the same individual, but for the different equations are correlated. However, we're also saying, moreover, I guess we're saying again, and that is kind of consistent with the structure of the cross-sectional data. We don't have correlation across individuals within the same equation, or we do not have correlation between different individuals across the different equations. Okay, so that's kind of like, this is the key assumption of SUR. So let's see if I can give you more intuition if I write the actual structure of the variance covariance matrix for all of the equations in the system. So let's look at E that E prime. So let's think about the variance covariance matrix of the errors, of all the errors in the demand system, in the equation, in the system of equations. Thinking about demand, that it could be any system of equations. Conditional x1 and up to xn. And sometimes, to save space, I'm going to just add a dot there. So this is going to be equal to the expected value. And let's see, what do we have here? So first we have E1, and this is the vector of errors for the first equation. Have E2, which is the vector of errors for the second equation. Have to E, say M equations. Okay, so remember these are vectors. We're multiplying this, so this is going to be, that's E. So we have T1 prime, this is going to be 1 by T, T2 prime, this is going to be 1 by T, and so on and so forth up to En prime, which is going to be 1 by T. Okay, so conditional on all the explanatory variables, like alpha dot. So if we were, if you think about it, so this is a vector, this is also a vector. So let's try to do the multiplication of these vectors. So the expected value of the product of these vectors is equal to the expected value, and we can use the products of each of those vectors. So it's going to be E1, E1 prime, E1, E2 prime. So remember, this is T by 1 times 1 by T. So this is going to be T by 1 times 1 by T up to E1, En prime, conditional on all those variables. Here we're going to have E2, E1 prime, E2, E2 prime, and so on and so forth until we get to En, En prime, En, E1 prime. Okay? Now, I had a student a couple of years ago who helped me to look at the products of all these products. And I have this handout that I sent it to you. Please give me a second because the computer is saving, taking some time. Okay, so look here what we have. So this is basically those products. So from this first matrix we have E1, E1 prime, and this one is E1, En prime. Okay, so if you think about that, so remember that what's going on here is that as showed you before, E1 includes E11, E12 up to En. Okay, so E1 is itself a vector. Is T1 by 1, this is 1 by T, so that's why we end up with this T by T matrix. Okay, so remember, one way to think about it is this is the matrix, that's the variance covariance matrix that we have for our individual equation previously. And remember, previously, if we assume homoscedasticity, we were assuming that all the diagonal elements in this matrix, all of these were equal to 0, 0, 0. And all the elements that were in the diagonal were a constant. Okay, so now we're going to be calling this sigma 1, 1 instead of sigma square. We use 1, 1. So actually, if we go throughout all the diagonal, again, going back to our matrix, so these are the elements in the diagonal. So you see all these products in the diagonal correspond to the variance covariance matrix of the errors for each of the equations separately. Okay, so again, this one will be exactly the same thing. So here we have an N, this will be equal to an N, and everything else will be 0 since we're assuming homoscedasticity within each equation. Okay, so if we do that, that's kind of how is that we end up with this matrix here and the diagonal and this matrix here. Okay, so now let's think about what's going on with this off diagonal element. So let's say at this specific product here. So we have the product of the errors of the first equation and the first individual, and the errors of the n equation for the first individual. Okay, so notice that the equation is the first one, this is the n equation, and this is the same individual. So, since we have the same individual, we're assuming that these errors are correlated, and that's what we will call sigma 1n. Okay, and again, all the diagonal elements, and this is kind of like another form of homoscedasticity because we're assuming that this correlation is kind of constant. Okay, but now let's look at this second element just for the sake of example. So we have the first equation, the first individual, and then we have the error of the n equation of the second individual. So remember that even within the same equation, we're assuming that you know the, the errors across different individuals are not correlated. Well, here we have the errors for different individuals in different equations. Okay, and of course that we're also assuming that they are uncorrelated, so that's equal to zero. So again, all the off diagonal elements are zero. Okay, so this is kind of like the key assumption of SUR, and I want you to be thinking about it a little bit further. Because I mean, if we go through all these little matrices, basically what went up is went up with this kind of block diagonal type of variance covariance matrix for the errors of all of the equations. Again, so this reflects homoscedasticity. This reflects homoscedasticity for the first equation, homoscedastic error for the n equation, and of diagonal elements. There's this assumption of correlation of observations for the same individual across equations. But I mean, we're assuming that the observations, the errors for different individuals are not correlated within the equation or across equations. Okay, so that's kind of what's going on here. This is the basics for even the construction of later on our estimators. So it's important for you. I really want you to be thinking about this issue very carefully. And as I was telling you before, basically all those equations are summarized in this third characteristic of assumption or the SUR model. Disturbances are correlated across observations, but correlated across equations. Um, okay, so that's kind of like a summary of that assumption. Okay, so let's see how is that we can go about estimating. I mean, the coefficients in this model. Okay, and of course, for estimation, we'll be using a GLS estimator for beta in SUR. Yeah, and what do we call beta? Beta is going to be the vector that includes the coefficients of all the n equations in the Riemann system. Okay, so how do we go about estimating? Okay, now let's think about, as usual, I mean, what we already know. Well, actually, what we could do, if you think about that, I mean, we have these n equations, we could be using, least squares to estimate each equation separately. And actually, it happens that equation by equation estimation of uh, the SUR system using least squares is actually consistent. But the problem is the lack of efficiency. Okay? And the lack of efficiency has to do inefficient due to the fact that we are not considering that the structure of the variance covariance matrix of the error. Okay? So actually to improve efficiency, to get more efficiency in the estimator, or to get an estimator that's more efficient, we can use the most efficient estimator, which is generalized least squares. Okay, now how does that work? Before we do that, let's write a generalized linear regression model for SUR. Generalized linear regression model for SUR. Okay, in order to do that, we basically what we have to do is we have to combine all of our questions. So what we're going to be doing is we're going to be stacking all the dependent variables. So this is going to be t by 1. Then we will have, so actually, this is the way that you should arrange your data if you want to use the generalized least square estimate. If you're thinking in terms of Excel, what you are doing here is you are putting all your dependent variables one under the other. Okay, so if you have 1,000 observations for each equation, you have 10 equations, so you're going to have 10,000 observations. That's kind of what's going on here. So we have mt plus 1. So that's equal to, and here what you will need to do is you need to create kind of like a diagonal type of matrix. So here you have t times k1, and then you have to have zeros. So let's put the place. In the diagonal you have all the matrices, so it's going to be t times k2, t times km. So notice that here we're making it possible for each matrix to have a different number of explanatory variables. Okay, so this is like a huge matrix that we'll have to construct. 1, t times k1, and so on and so forth. And then here we will have the matrix with the coefficients. This is our delta matrix. 10. So now what are the dimensions of this matrix? Is going to be mt times, is going to be the sum of all the ki's, and it's going to be the sum of all the ki's, because remember we're assuming the betas can have different dimensions, and we also have the error, which can all the matrix of those errors stack. And this is going to be the same dimensions as y and t times 1. Okay, so remember here the dimensions of this one is k1 by 1, k2 by 1, kn by 1. Okay, so that's what here we have the sum of all the ki. Okay, so in matrix form we can write this as y equal to x beta plus error term, and we know the structure of the variance covariance matrix of these errors that we can call omega without like b vector of errors. So basically, when we write it in this way, this is just like a generalized linear regression model. So then the dimensions is going to be mt times mt. GLS estimator is so what's called SUR. Well, actually, so this is gonna be a bit color, but I'm gonna write SUR. SUR is gonna be the generalized score estimator. H prime sigma x inverse x prime sigma y. Now it can be shown that actually this can be a bit simplified since we have um, the structure of sigma is kind of unique since it's kind of like that diagonal matrix structure, and I'll explain that in a second. Um, what is that? So, but we cannot make use of that unique structure to rewrite thing that I'm missing here is an inverse, and I'll explain you what is the sigma times I inverse y. Okay, so we can rewrite it that way since our omega equal to the product of sigma, and this is kind of the Kronecker product, and I'll give you some intuition of what's going on there. And of course, the inverse of sigma is the inverse of this omega matrix times the Kronecker product of the matrix sigma and an identity matrix. So this is what's called Kronecker product. Okay, and I'll give you some intuition in a second. But what's that sigma matrix? You see that sigma matrix is just a matrix of all those coefficients that come from that very large uh, variance covariance matrix of error. So sigma 1, sigma 1, 2, up to sigma 1m, sigma 2, 1, sigma n1. So this is n by n. So remember, if we go to our variance covariance matrix, you see where the thing is coming from. Okay, so our omega matrix here would include all those sigma coefficients, 1n, 2, 1, n, and 1, n, and this is supposed to be here, dots. Okay, and this should be the Kronecker product of an identity matrix that it has to be here, T by T. So what this Kronecker product does, basically what it's doing is multiplying each of these coefficients times the identity matrix and make it a B. So with the Kronecker product, we go from this n by n matrix to this matrix that is mt times mt. This is kind of like the Kronecker product allows us to expand that matrix. So again, each of these terms becomes like a big diagonal matrix. So that's kind of what's going on with that Kronecker product. So it's a simpler way to write these metrics. And also, later on I'll talk about like for estimation purposes, that really simplify estimation. And how is that going to be simplifying estimation? Well, because that here in the GLS model, you see this matrix sigma is mt times mt. So to apply this estimator, we'll have to calculate the inverse of a matrix that is mt by mt. And let's say if you have 10,000 observations, so you have 10 equations, that's basically that metric to be 100,000 by 100,000. So to calculate the inverse of a matrix that's 100,000 by 100,000, I mean, even with today's computers, it's a very difficult task. On the other hand, you see, we use these Kronecker products, calculating the calculating the inverse of a matrix that's 10 by 10. I mean, that's very easy. I mean, you could even do it by hand. It's not that easy, but it's even feasible to do it by hand. So that's kind of why we rewrite the question in that form. Okay, so that is the estimator, but of course, this is kind of the GLS estimator where we're assuming that we know the structure. So later on, we will talk about the physical general square estimator, but that gives us an idea of what we need to do. Okay, now, question that is, I think, that we're asking is the following. Now, we know that the questions are linked by the errors. So the question is how much efficiency is gained by using this generality square instead of the question by question OLS. Okay, so how much efficiency is gained by using GLS instead of the question by question OLS. Least square estimate. Well, if the questions are unrelated, so if the questions are unrelated, basically if all those coefficients are equal to 0, or I different than j, because only the correlations, I mean, the off-diagonal elements of this matrix, the diagonal elements of those correspond to the variance, and that cannot be 0. There is no gain in using GLS. In using GLS. Now, actually, there is even a test that allows you to see if um, you know those off-diagonal elements are equal to 0. Now, the reality is that in practice, SUR is the default estimate. So I used to teach that test, but GLS is the default estimate. That's what everybody is using. I mean, so you don't gain efficiency, but you don't lose any efficiency on the other hand. So in practice, SUR is the default estimate. Okay? Now, second case. If the questions actually have the identical explanatory variables, then GLS and OLS are identical. If the questions the questions I wanted to see what's the time, and so if the questions have identical explanatory variables, identical explanatory variables, that is xi equal to x, then GLS and OLS are identical. So what this is saying is that if you have all of the equations have exactly the same set of explanatory variables, you could use OLS or you can use DLS. And actually, not even once I have a paper, but I mean they are exactly the same thing. So, but so you could use one or the other. But once I had a paper and I was using SUR, and the reviewer insisted that I use OLS instead of using SUR, even though I was telling them that I knew that I was not getting anything with using SUR. It doesn't matter if they were identical, but he had me using OLS. No, but there is an exception. And this is a very important exception. This OLS are identical, except, and this is a very important exception, especially for demand analysts or people like me that do demand analysis. This is except in the case when there are restrictions of the coefficients across equations. And I'll give you an example of what I mean by this. What does it mean? I mean, hopefully you all understand that you can have the same dependent variable with the same explanatory variables, and actually that's kind of the example that I was giving you for demand system. So you might be wondering what's going on. So you see here we have the dependent variables were different, but the explanatory variables were the same. So you would say, well, I mean, that means then that if there are not, that, basically it doesn't make it, what's the point of using SUR if actually they have identical? Well, it happens that actually in the demand system of equations, some of the coefficients of one equation are related to the coefficients of the other equation. Let me write down, the example there. So again, let's use that as an example. And let's use a demand system with shares. So it's a demand system with shares. With those taking a demand class with Dr. Chini, probably, they would see some demand systems that more than like that. So we have, the first demand system is the share for the first group, coefficient. Then you have the first price, second price, and we were talking about, in that example, four prices. Four prices. Be there, but it doesn't look nice. Okay. Maybe carrying up a little bit. Let's break that one for before. Oh, let me see. This is the income term plus alpha 1 I. So that's the income, the first error. So you see now, so this is the first equation. So it's the share for the first good as a function of the prices of the four goods and income. We can write the equation for the second good. Again, we're going to have exactly the same explanatory variables. Of course, the coefficients are going to be different. And, we can write up to the four equations. T1, T1, T4, T2, actually, let me see, for 1 should be 4, 2, 4, 2, 4, 2, P2, 4, 4. So in a demand system of equations, to be consistent with demand theory, we, for example, have something that are called the symmetry restrictions. Okay? You see in these symmetry restrictions, for example, the first, the coefficient of price in the first equation has to be equal to the second equation. Well, let me see. What's going on here is the effect of price for the first good has to be equal to the effect of price of the first good on the second good. And also, like effect of price of the price 3 on the first good has to be equal to the effect of price of the first good on the share of the third good. In that, we can write all of these equations, all of these restrictions for all of the goods, and so on and so forth. They're going to be now, like for second good, so it's going to be 3, 2, 2, 4 equal to 4, 2. So you see how these coefficients are related across equations because those effects are constrained to be correlated across these different equations. Okay, so that's kind of the case where I was saying that if that's the case, so even though the equations have identical explanatory variables, since the coefficients are restricted, to be similar across the different equations, then there is gain of efficiency. There are efficiencies to be gained. So that's what I mean here. This is a very relevant example, and actually we will be using in our lab. We will be using these demand systems as an example. Okay, so before we talk about the theoretical, the general least square estimator. So now let's talk about feasible general least square. Or even though I would call it feasible SUR, but in practice everybody actually the feasible SUR is called just SUR. So how do we go about estimating this feasible general least square in the context of SUR? So step one, so what we do is we would use OLS to estimate each equation separately. Step two, we use the OLS residuals from each equation to estimate the elements of that sigma matrix. And this is kind of like some sort of, it's the kind of, the way to think about that is an estimate of the correlation of the errors across equations. So sometimes Sij, that's going to be the product of the OLS residuals from the first equation and the residuals from the J equation divided by T, which is the same as the product of A by T and T over T. And when we have AI, we just remember the errors of the data obtained using least square estimate. So remember, this is a t by 1, and these terms here are the elements of, of that metric. So what we're doing basically is we're multiplying. If you think about here, what we're doing here is we're multiplying the errors from the residuals for the same individual across the different equations. And that's kind of what that gives us, that estimate, kind of the correlation of the errors across the different equations. So once we have that, I mean, we have a sigma hat matrix. So you see, this is the estimated one. Mm, one, two, and so on and so forth. Okay, so once we have that, in step 3, actually this is very easy. We have a feasible generalized feasible GLS, which is, it's called SUR. And I apologize because usually, it's not called feasible SUR. SUR is just SUR. The previous one should be called the theoretical SUR. And that should be equal to X prime. And once again, we should substitute that sigma we had. Conical product of the identity matrix, inverse, X, inverse, prime. Well, actually, here, I'm going to make this smaller because I'm running out of space. So I will do it again. So this is X prime. So this is the inverse sigma and the conical product of the identity matrix, X, X prime, and the matrix times Y. And remember that here, this is the estimate of sigma hat inverse. Okay, so actually it's pretty straightforward. It's not that difficult to implement it. So I would see, I'll think about that. Maybe I ask you to implement it using simulations. I'll check. I need to give you feedback regarding those homeworks. And after I've done that, I'll think about maybe we do some exercise. And then for testing hypothesis, we use, um, depending, for small or moderately sized samples, we can use like an S test, 1 divided by J. And you probably remember from Dr. Chimney class, we have this R, matrix of restrictions. Remember how to work with the restrictions using this R, big R matrix and this Q matrix times R, the variance of beta, hat, prime inverse, times R beta minus Q. Okay, so it can be shown that F hat value follows at F distribution with J and C degrees of freedom. Okay, where J is the number of restrictions. Remember, C is the number of observations that we have. And then restrictions. So for small or moderate sample size, we know that that F statistics follow a net distribution, but for large sample size, JF hat follows a chi-square distribution with J degrees of freedom. Okay, now the good thing is that you won't have to model most of the time these tests. So for the lab, the lab will teach you how to estimate demand systems using SUR, and the tests are given to you. But it's good to have an idea of how these tests are conducted in the context of SUR. But the point here of these metrics, I guess, more than I mean, for you to get kind of confused using all of this terminology, is that the test of restrictions is very similar to the way that you do it in the context of a simple equation. Remember, the idea here is that once we have this generalized regression model, what we do is we create this huge y metrics, we create this huge x metrics, and then we create this huge beta metric, which includes the coefficients of all of the equations. And that's more or less what I want you to show you here. That intuition to do test of hypothesis for restrictions in the context of the simple linear regression model is very similar to the way that we do it in the context of systems of equations, especially in the context of the similarly unrelated regression. So I think that that's kind of what I have for you regarding the similarly unrelated regression. So at first, we define what was the similarly unrelated regression. Basically, we have several equations. We talk about the main assumptions. So we assume exogeneity, homoscedasticity, and the main assumption has to do with the relation of the errors for the same individual across equations, and we look at the structure of those errors. So once we understand that structure, basically we realize that the SUR system can be written as a generalized linear regression model, and we can use uh, generalized least squares for estimation. And then we can learn also to see which are the steps to apply the physical generalized least square estimate. And in terms of tests, the intuition and the tests are very similar to the one that we use in the context of simple linear regression. Okay, so that's basically what I have for you regarding this topic.